Tonight, we're going to talk about something that keeps astronomers up at night. Not because they're scared, but because they're confused. Actually, genuinely confused. Because out there in space, we've discovered things that don't make sense. Things that shouldn't exist, according to everything we know. Things that break the rules. And I'm not talking about science fiction. I'm not talking about theories or speculation. I'm talking about real observations. Things we've actually seen and measured. Things that are out there right now, doing whatever strange thing they do, and we have no idea why. Over the past few decades, as our telescopes have gotten better and our ability to observe the universe has improved, we've stumbled across discoveries that have left scientists scratching their heads. Some of these discoveries challenge our understanding of physics. Some of them suggest there might be processes in the universe we don't know about yet. And some of them are just plain weird. Before we dive in, if you enjoy these deep explorations into the mysteries of space, a quick like or subscribe would really help the channel. It's a small thing, but it makes a big difference. Now, let's get into it. Let me start with something that happened on August 15th, 1977. A man named Jerry Ehman was reviewing data from the Big Ear radio telescope at Ohio State University. The telescope was part of SETI, the search for extraterrestrial intelligence. Every day, it scanned the sky, listening for radio signals that might indicate intelligent life somewhere out there. Most days, the data was boring. Background noise from space, nothing unusual. But on this particular day, Ehman saw something that made him grab a red pen and write, "Wow," in the margin of the printout. That's why we call it the wow signal. The signal lasted 72 seconds. During that time, it was 30 times stronger than the background noise. It came from a specific direction in the constellation Sagittarius. And here's what makes it so interesting. The signal's frequency was around 1420 megahertz. That's right near the hydrogen line, a natural frequency associated with hydrogen atoms. Why does that matter? Because hydrogen is the most common element in the universe. If you were an alien civilization trying to send a signal that other civilizations might recognize, you might choose a frequency related to hydrogen. It's like choosing a universal language based on something everyone would know. The Big Ear telescope had two receivers that scanned the same patch of sky 3 minutes apart. The signal showed up on the first receiver, but not the second. That means it lasted less than 3 minutes, probably closer to 72 seconds based on the data we have. Since 1977, astronomers have gone back to that same spot in the sky dozens of times. They've used more powerful telescopes. They've listened at the same frequency and nearby frequencies. They've searched for any sign of the signal returning. Nothing. The wow signal was a one-time event. Now, let me be clear about the uncertainty here. The signal could have been artificial or natural. The Big Ear telescope couldn't pinpoint locations precisely, so we know the general direction but not the specific source. Some scientists have proposed natural explanations. Maybe it was a signal from a passing comet. Comets can emit radio waves when the solar wind interacts with their hydrogen clouds. In 2016, a researcher named Antonio Paris suggested that two comets, known as 266P/Christiansen and P/2008Y2, were in that region of space at the time. But there's a problem with the comet theory. The signal was incredibly narrow band. It occupied a very specific frequency. Natural sources usually produce signals across a broader range of frequencies. The narrowness of the wow signal is more consistent with an artificial source, something deliberately transmitting on a chosen frequency. Other scientists have suggested it might have been interference from Earth. A satellite or aircraft or some ground-based transmitter that happened to send a signal at just the right time. But the Big Ear telescope was designed to filter out terrestrial interference. And the signal came from a direction that was not consistent with any known satellite or aircraft at the time. So what was it? Honestly, it remains unexplained. And that's what makes it so fascinating. Nearly 50 years later, the WOW signal remains one of the most intriguing, unexplained observations in the history of SETI. The fact that it never repeated is both frustrating and significant. If it was an alien civilization, why would they only transmit once? Maybe they were using a lighthouse strategy, sweeping a beam across the galaxy, and we just happened to catch it for a brief moment. Maybe it was a one-time broadcast. Maybe it wasn't meant for us at all, just an accidental spillover from some other communication. Or maybe it wasn't aliens at all. Maybe it was some natural phenomenon we don't understand yet. The universe is full of processes that emit radio waves. Pulsars, quasars, magnetars, supernova remnants. We're constantly discovering new types of radio sources. Maybe the WOW signal was something natural that we've just never seen before or since. The truth is, the answer may never come. The signal lasted 72 seconds in 1977 and never came back. It's a mystery frozen in time. But it's also a reminder of how much remains unexplained about the universe. Somewhere out there in the direction of Sagittarius, something sent out a powerful, narrow-band radio signal, and we happened to catch it. That's either the most incredible coincidence in the history of astronomy, or it's evidence of something extraordinary. Either way, it's strange. And it's why, almost 5 decades later, people are still talking about the WOW signal. Now let's talk about something that's happening right now. A star that's been driving astronomers crazy since 2011. Its official name is KIC 8462852, but most people call it Tabby's star, named after astronomer Tabby, who led the research team studying it. Tabby's star sits about 1,460 light-years away in the constellation Cygnus from Earth. It looks like an ordinary star. It's slightly larger and hotter than our Sunday. Nothing about it should make it special. But in 2011, the Kepler Space Telescope noticed something weird. Stars dim sometimes. That's normal. If a planet passes in front of a star from our perspective, the star's light drops slightly. That's how we detect exoplanets. When Earth passes in front of the Sun from another star's perspective, the Sun's light would dim by about 0.01%, tiny but measurable. Jupiter, being much larger, would cause the Sun to dim by about 1% if it passed in front. That's the kind of dimming we expect from planets. Regular, predictable, small. Tabby's star doesn't do that. In 2011, its light dropped by 15%. Then it came back. In 2013, it dropped by 22%. Then it came back again. The dimmings were irregular. They didn't repeat at predictable intervals. They lasted different amounts of time. Sometimes the star would dim a little, sometimes a lot. 22% is enormous. That's not a planet. A planet the size of Jupiter would only block 1% of the star's light. To block 22%, you'd need something absolutely massive. Something as large as the star itself. The initial discovery set off a frenzy of theories. What could be blocking the light? Here's where things got really interesting. Someone suggested it might be an alien megastructure. The idea comes from a hypothetical concept called a Dyson sphere, proposed by physicist Freeman Dyson in 1960. Dyson wondered what an advanced civilization would do if it needed enormous amounts of energy. Eventually, he reasoned, they might build structures around their star to capture its energy output. Not a solid shell, which would be impossible, but a swarm of energy collecting satellites orbiting the star. If you were building something like that, it would block varying amounts of the star's light as the structure orbited. It would be irregular. It would dim the star by large amounts. It would look exactly like what we were seeing with Tabby's star. Now, before you get too excited, let me be clear. Most astronomers don't think Tabby's star is an alien megastructure. The alien hypothesis was always the least likely explanation. But here's the thing. We had to consider it because we couldn't explain the observations any other way. That's how weird this star is. So, if it's not aliens, what is it? Scientists proposed several natural explanations. Maybe there's a giant swarm of comets orbiting the star. If a family of comets passed in front of the star, they would block light irregularly. Their dust tails would create uneven dimming. This was a leading theory for a while. But there are problems with the comet theory. Where did all these comets come from? You'd need an enormous number of them to block 22% of the star's light. And comets would produce dust, which would make the star appear redder when it's dimmed. Tabby's star doesn't do that. The color stays the same even when it's dimmed. Another theory suggested maybe there was a recent collision. If two large objects smash together near the star, the debris cloud could block light irregularly as it spreads out. But again, we'd expect to see excess infrared radiation from warm dust. We don't see that. Some scientists suggested the dimming might be caused by the star itself. Maybe it's a variable star that dims naturally. But Tabby's star doesn't show the characteristics of known variable stars, and the dimming pattern is too irregular. Then in 2017, astronomers made another observation. They caught Tabby's star dimming again and observed it across multiple wavelengths of light. What they found was interesting. The dimming was more pronounced in blue light than in red light. That's consistent with dust blocking the starlight. Small dust particles scatter blue light more effectively than red light. It's the same reason Earth's sky is blue. So maybe it is dust after all. But if it's dust, where's it coming from? Why is there so much of it? Why is the pattern so irregular? The latest observations suggest that Tabby's star might have a large debris field around it. Perhaps from a destroyed planet, or a massive collision, or some other catastrophic event. The debris blocks light irregularly as it orbits. This is the current leading explanation, but it's not fully satisfying. The full picture remains unclear. And here's what makes this even stranger. Tabby's star is still doing it. We've now watched this star for more than a decade. It keeps dimming in weird, unpredictable ways. We have multiple data sets from different telescopes. The phenomenon is real. It's not a measurement error. It's not a glitch. Something is actually blocking the light from this star in ways that remain puzzling. As of 2025, Tabby's star remains one of the strangest objects in the sky. Out of hundreds of billions of stars, this is the only one that behaves like this. We've never seen anything else quite like it. Maybe one day we'll figure it out. Maybe we'll discover it's a natural process we just haven't encountered before. Or maybe, just maybe, it's something else entirely, something we haven't even thought of yet. Let me tell you about something that scientists discovered in 2019 that absolutely shouldn't exist. They're called odd radio circles, or ORCs. The name is perfect because they are odd, they're circles, and we only see them in radio wavelengths. Here's what they look like. If you point a radio telescope at certain parts of the sky, you see a perfect circle. The circle is enormous, hundreds of thousands of light years across. And here's the weird part. There's usually a galaxy at the center. The first one was discovered by a team led by astronomer Ray Norris. They were using the Australian Square Kilometre Array Pathfinder Telescope, or ASCAP, surveying the radio sky. ASCAP is sensitive to radio waves, which means it sees the universe differently than optical telescopes do. When the team processed their data, they found these circular structures. At first, they thought it was a processing error. Circles are suspicious in astronomy. Nature rarely makes perfect circles. But when they checked the data carefully, the circles were real. They found 3 more. Then other telescopes confirmed them. As of 2025, we found about a dozen orcs. They're rare, they're large, and their origin remains a puzzle. Let me describe what we're seeing. Each ORC is a ring or shell of radio emission. The ring is nearly circular, sometimes perfectly so. At the center, there's usually an elliptical galaxy. The galaxy appears normal at optical wavelengths. There's nothing obvious about it that would explain the radio ring around it. The rings are enormous. Some are more than 1 million light-years across. That's 10 times the diameter of the Milky Way. These are huge structures. Now, astronomers see circular things in the sky sometimes. Supernova remnants can look circular. They're the expanding shells of debris from exploded stars. But supernova remnants are much smaller, and they're associated with recent stellar explosions. Orcs are too large and too far away to be supernova remnants. Planetary nebulae can also look circular. These are the shells of gas shed by dying stars. But again, they're much smaller, and they're in our galaxy. ORCs are definitely not planetary nebulae. Some galaxies have radio lobes, where jets from a central black hole shoot matter out into space. These can create circular structures when viewed from certain angles. But ORCs don't match the characteristics of radio galaxies. The central galaxies don't show the active supermassive black holes that would be needed to create such structures. So what are they? Honestly, we don't know. Scientists have proposed several theories. Maybe they're shockwaves from massive explosions in the center of galaxies. If a galaxy went through a period of intense star formation, or if its central black hole suddenly became active, it could create a blast wave that expands outward. Over millions of years, this wave could create a spherical shell of radio emission. But if that's the case, why don't we see more of them? Galaxies go through active phases all the time. We should see these structures more often. Another theory suggests they might be related to merging galaxies. When 2 galaxies collide, all sorts of crazy things happen. Maybe the collision creates shock waves that expand outward as spherical shells. But again, galaxy mergers are common. Orcs are rare. Some scientists have suggested even more exotic explanations. Maybe they're the imprints of primordial events from the early universe. Maybe they're related to cosmic strings or some other esoteric feature of space-time. These ideas are pretty speculative. The truth is, we're still in the discovery phase with ORCs. We've only known about them for a few years. We need more observations. We need to find more of them. We need to study the galaxies at their centers in more detail. What makes orcs particularly fascinating is that they represent something new. We've been studying the radio sky for decades, but ORCs only showed up when we built more sensitive radio telescopes. They were always there. We just couldn't see them until recently. This tells you something important about astronomy. The universe is full of things we haven't discovered yet, not because they're hiding, but because we don't have the tools to see them. Every time we build a better telescope or observe in a new wavelength, we find something unexpected. ORCs are a perfect example. Nobody predicted them. Nobody was looking for giant radio circles around galaxies. They were a complete surprise. And now astronomers are trying to figure out what they are, and what they tell us about the universe. As of 2025, ORCs remain unexplained. We know they exist. We know roughly what they look like, but we don't know what causes them. There's strange structures in the radio sky, and they're waiting for someone to figure them out. Now let's talk about something that breaks the rules on a truly cosmic scale. In 2021 and 2024, astronomers discovered two enormous structures that challenge one of the fundamental principles of cosmology. The first is called the Giant Arc. It was discovered by Alexia Lopez, a PhD student at the University of Central Lancashire. The Giant Arc is a structure of galaxies that spans about 3.3 billion light-years. That's not the distance to it, that's how large it is. The structure itself is 3.3 billion light-years across. To put that in perspective, light takes 3.3 billion years to travel from one end of this structure to the other. The entire observable universe is only 93 billion light-years across. This structure is a significant fraction of that. The Giant Arc is located about 9.2 billion light-years from Earth. It appears as a curved arrangement of galaxy clusters, like a giant arc in the sky. Hence the name. Then in 2024, the same research team found something else. They call it the Big Ring. This is another enormous structure, about 1.3 billion light-years in diameter. It's also located about 9.2 billion light-years away, and here's the kicker. It's in the same region of the sky as the Giant Arc. So we have two enormous structures, both in the same part of the universe, both at the same distance. That's suspicious. It suggests they might be related somehow. Now, why is this a problem? Let me explain. In cosmology, there's something called the cosmological principle. This principle states that when you look at the universe on large enough scales, it should be roughly uniform. No matter which direction you look, you should see roughly the same density of matter. The universe should be homogeneous and isotropic at large scales. This principle is fundamental to our understanding of the universe. It's built into the standard model of cosmology. It's supported by observations of the cosmic microwave background, which shows that the early universe was remarkably uniform. But the Giant Arc and the Big Ring challenge this principle. They're too large. According to calculations based on the standard model, structures shouldn't be able to grow larger than about 1.2 billion light-years. That's the theoretical limit, based on how gravity has had time to pull matter together since the Big Bang. The Giant Arc is nearly 3 times larger than this limit. Even the Big Ring, at 1.3 billion light-years, is pushing the boundary. If these structures are real, and they appear to be, then either our theoretical limit is wrong or something weird is going on. Maybe the cosmological principle doesn't hold as well as we thought. Maybe the universe is lumpier than we believed. Maybe there are processes we don't understand that can create structures larger than theory predicts. Some astronomers have questioned whether these structures are real or just statistical flukes. When you look at the distribution of galaxies, you can sometimes see patterns that aren't really there. Your brain looks for connections. You might see a line or arc of galaxies that's just a coincidence. But Alexia Lopez and her team did careful statistical analysis. The probability of the Giant Arc being a random arrangement is about 1 in 6,000. That's pretty low. The structure appears to be real. The Big Ring's statistics are even more compelling, and the fact that both structures are in the same region of space makes a coincidence less likely. So what are they? One possibility is that they're related to something called baryon acoustic oscillations. In the early universe, sound waves traveled through the hot plasma. These waves left an imprint on how matter is distributed. They create a preferred scale, a characteristic size for structures. But the giant arc and the big ring don't match the expected size from baryon acoustic oscillations. They're much larger. Another possibility is that they're related to cosmic strings. These are hypothetical, one-dimensional defects in space-time, predicted by some theories but never observed. If cosmic strings exist, they could create large-scale structures as galaxies form preferentially along them. But cosmic strings are speculative. We have no direct evidence they exist. The most troubling possibility is that our cosmological model is incomplete. Maybe the cosmological principle isn't as robust as we thought. Maybe the universe has large-scale structure that we didn't account for. Maybe at the largest scales, things are more complex than our models predict. This wouldn't mean the Big Bang theory is wrong. It would mean we need to refine our understanding of how structure formed in the universe. That's how science works. You make observations, build models, and when observations don't match models, you update the models. As of 2025, the giant arc and the big ring remain controversial. Some astronomers are convinced they're real structures that challenge the cosmological principle. Others are more skeptical, thinking they might be statistical anomalies or misinterpretations of the data. What's clear is that the universe at the largest scales is more complex than we thought. And these enormous structures, whether they turn out to be real anomalies or something else, are pushing us to think harder about how the cosmos is organized. Let me tell you about a place in the universe that's almost empty. It's called the Boötes void, and it's one of the strangest features of the cosmic landscape. The Boötes void is a region of space about 330 million light-years across. To put that in perspective, that's more than 3,000 times the diameter of the Milky Way. It's an enormous volume of space. Here's what makes it strange. This volume should contain about 2,000 galaxies. That's what we'd expect based on the average density of galaxies in the universe. But when astronomers survey the Boötes void, they find only about 60 galaxies. The rest is empty. It's not completely empty. There are a few dozen galaxies scattered throughout, but compared to what should be there, it's remarkably void of matter. That's why we call it a void. The Boötes void was discovered in 1981 by astronomer Robert Kirshner and his colleagues. They were mapping the distribution of galaxies and noticed this huge empty region in the constellation Boötes. Initially, they weren't sure if it was real or just an artifact of their survey. Maybe they had missed some galaxies. Maybe their detection methods weren't working properly in that region. But follow-up observations confirmed it. The void is real. There really is a huge bubble of space with almost no galaxies in it. Now, voids are not unusual in the universe. The cosmic web I mentioned earlier consists of filaments of galaxies surrounding voids. Most voids are tens of millions of light-years across. They're pretty common, but the Boötes void is special. It's much larger than typical voids. It's one of the largest known supervoids in the nearby universe, and its existence raises questions about how structure formed in the cosmos. Here's the thing. The universe started out almost perfectly uniform. The cosmic microwave background shows us that at 380,000 years after the Big Bang, matter was spread almost evenly throughout space. There were tiny density variations, but they were incredibly small. Over time, gravity amplified these variations. Regions that were slightly denser attracted more matter and became even denser. Regions that were slightly less dense lost matter to their surroundings and became voids. Computer simulations of this process can reproduce the cosmic web we see today, Filaments, clusters, and voids all emerge naturally from gravity, acting on the initial density variations. But the simulations also predict limits. Voids can only grow so large given the age of the universe and the strength of gravity. The Boötes void is close to this limit. It's about as large as voids can theoretically get. That makes it interesting because it's an extreme example. It's testing our understanding of structure formation. If our models are correct, we shouldn't see voids much larger than the Boötes void. If we do, it would suggest something is wrong with our models. So far, the Boötes void fits within theoretical limits, but it's close to the edge. And that makes it worth studying carefully. There's another interesting aspect to the Boötes void. The few galaxies inside it are weird. Some of them are forming stars at unusually high rates. Some have unusual shapes or characteristics. It's like the isolation has affected them somehow. Think about it. If you're a galaxy in a dense region of space, you're constantly interacting with other galaxies. You're pulling on them gravitationally. Sometimes you collide and merge. You're exchanging gas. You're part of a busy neighborhood. But if you're a galaxy in the Boötes void, you're alone. Your nearest neighbor might be millions of light years away. You're evolving in isolation, without the gravitational harassment that galaxies in dense regions experience. This isolation might change how you evolve. Maybe you retain more gas because nobody is stripping it away. Maybe your star formation happens differently. Maybe you develop unusual characteristics. The galaxies in the Boötes void give us a chance to study what happens to galaxies when they're isolated. It's a natural experiment that the universe has set up for us. But the fundamental question remains: why is the Boötes void so empty? Why did this particular region of space end up with so few galaxies? The answer probably goes back to the initial conditions of the universe. This region must have started out with a slightly lower density than average. Over billions of years, gravity pulled matter out of the region toward denser areas, creating the void we see today. But why was this region less dense to begin with? That's a deeper question. It relates to whatever process created the initial density variations in the very early universe. Most cosmologists think these variations came from quantum fluctuations during the inflationary epoch, a brief period of exponential expansion right after the Big Bang. These quantum fluctuations were random. Some regions ended up slightly denser, some slightly less dense. Most variations were small, but occasionally, by chance, you'd get a larger variation. The Boötes void might be the result of one of these chance larger variations in the initial conditions. It's remarkable when you think about it. The emptiness we see in the Boötes void today, 330 million light-years across, originated as a tiny quantum fluctuation in the first fraction of a second after the Big Bang. That microscopic variation has been amplified over 13.8 billion years into this enormous supervoid. The universe is strange like that. The smallest things can have the largest consequences given enough time. Speaking of the early universe, let me tell you about one of the most peculiar features in the cosmic microwave background. It's called the CMB cold spot, and it's been puzzling cosmologists since 2003. The cosmic microwave background, or CMB, is the afterglow of the Big Bang. When the universe was 380,000 years old, it cooled enough that electrons and protons could combine to form neutral hydrogen. Before this, the universe was opaque. Photons couldn't travel far before hitting free electrons. After this, the universe became transparent. Photons could travel freely. The CMB is made of these photons. They've been traveling through space for 13.8 billion years. We see them today as a faint microwave glow coming from all directions in the sky. The remarkable thing about the CMB is how uniform it is. If you measure its temperature in different directions, it's almost exactly the same everywhere, about 2.725 Kelvin, just a few degrees above absolute zero. But there are tiny variations. Some regions are slightly warmer, some slightly cooler. The temperature differences are about 1 part in 100,000. These variations are the imprints of density fluctuations in the early universe. Regions that were slightly denser were slightly cooler in the CMB. These dense regions eventually became the galaxies and galaxy clusters we see today. So the CMB is incredibly important. It's a snapshot of the universe when it was just 380,000 years old. By studying the pattern of hot and cold spots, we can learn about the initial conditions of the universe. Satellites like COBE, WMAP, and Planck have mapped the CMB in exquisite detail. And when scientists analyzed these maps, they found something unexpected. There's a region of the sky, about 10 degrees across, that's significantly cooler than expected. This is the CMB cold spot. It's not just a little bit cooler, it's about 70 millionths of a degree cooler than the average. That might sound small, but in the context of the CMB's tiny variations, it's huge. The cold spot is located in the constellation Eridanus. It's oval-shaped, spanning about 10 degrees by 5 degrees. That's roughly 50 times the apparent size of the full moon. Here's why it's strange. Based on our standard model of cosmology, we can calculate the probability of such a large, cold region appearing by chance. The probability is about 2%. Not impossible, but unlikely. 2% means that if you ran the universe 100 times with random initial conditions, you'd expect to see a cold spot like this in about 2 of those universes. We live in one universe. So either we're just unlucky and happen to be in one of the 2%, or there's something special about the cold spot. Scientists have proposed several explanations. One idea is that the cold spot is caused by a supervoid. Remember, voids are regions of space with few galaxies. If there's an enormous void between us and the CMB in this direction, photons passing through it would lose energy due to something called the integrated Sachs-Wolf effect. Here's how it works. As photons enter a void, they climb out of a gravitational well, losing energy. As they leave the void, they fall into a gravitational well, gaining energy. If the universe weren't expanding, these effects would cancel out. But because the universe is expanding, the void gets larger and less dense while the photons are crossing it. This means they gain less energy on the way out than they lost on the way in. Net result, the photons end up cooler. So a supervoid could create a cold spot in the CMB. And indeed, astronomers have found evidence of a large void in the direction of the cold spot. It's not as large as the Boötes void, but it's still substantial. But here's the problem. Even with this void, the calculations suggest it can only account for a small part of the cold spot's coldness. You'd need an absolutely enormous void to explain the full effect, and we don't see evidence of a void that large. Another theory suggests the cold spot might be related to a collision between our universe and another universe in a multiverse scenario. In some versions of cosmic inflation theory, our universe is just one bubble in an infinite foam of universes. If another universe bubble collided with ours early on, it would leave a mark in the CMB, a circular region that's colder or warmer than average. This is a pretty exotic explanation, and there's no direct evidence for it beyond the cold spot itself. But it shows how puzzled scientists are. They're willing to consider multiverse collisions because the conventional explanations don't quite work. A third possibility is that the cold spot is just a statistical fluke. 2% probability means it's rare, but not impossible. Maybe we just happen to live in a universe where this unlikely feature exists. Sometimes rare things happen. The challenge is that we only have one CMB to observe. We can't run the experiment again. We can't create 100 universes and see how many have cold spots. We have one data point, the universe we live in. This makes it hard to know if the cold spot is a meaningful anomaly or just chance. If we had 10 universes to observe and 9 of them had no cold spot, we could say with confidence that the cold spot in our universe is significant. But we don't have that luxury. As of 2025, the CMB cold spot remains unexplained. It might be caused by a supervoid, but probably not entirely. It might be a statistical fluke, but that seems unsatisfying. It might be evidence of exotic physics, but that's highly speculative. What's clear is that it's anomalous. It stands out in the CMB maps. It's larger and colder than our models predict. And until we have a convincing explanation, it remains one of the strange things in our universe that we don't fully understand. Now, let's talk about a star that breaks the rules of nuclear physics, or at least seems to. It's called Przybylski's star, officially designated HD 101065. It's located about 370 light-years away in the constellation Centaurus. From a distance, Przybylski's star looks normal. It's an A-type star, about twice as massive as the Sun and about 6 times more luminous. Nothing unusual there. But when astronomers analyzed its light spectrum, they found something absolutely bizarre. The star contains elements that shouldn't exist in any star for more than a few weeks. Specifically, it contains technetium, promethium, and other radioactive elements, with short half-lives. Let me explain why this is a problem. Stars create elements through nuclear fusion. In their cores, hydrogen fuses into helium. In more massive stars, helium fuses into carbon and oxygen. In the most massive stars, the process continues, creating heavier and heavier elements up to iron. Elements heavier than iron are created in supernova explosions and other energetic events. When a massive star explodes, the incredible pressures and temperatures create these heavy elements. They're scattered into space, where they can be incorporated into new stars. So when we see heavy elements in a star's atmosphere, we assume they were there when the star formed. The star was born from a cloud of gas that contained material from previous generations of stars, including their heavy elements. But here's the catch. Some heavy elements are radioactive. They decay over time. Uranium, for example, has a half-life of about 4.5 billion years. That means half of any uranium will decay into lighter elements in 4.5 billion years. But even after billions of years, some uranium is still around. Technetium, on the other hand, has no stable isotopes. All forms of technetium are radioactive. The longest-lived isotope, technetium-98, has a half-life of about 4.2 million years. That's nothing on cosmic timescales. Przybylski's star is probably several billion years old. Based on its characteristics, it's a mature star, not a young one. If it formed with technetium in its atmosphere, that technetium would have decayed away billions of years ago. There should be none left. Yet, when astronomers observe the star's spectrum, they see clear evidence of technetium. They also see promethium, another radioactive element with a short half-life. And they've seen these elements consistently since the star was first studied in detail in the 1960s. So where is this technetium coming from? There are a few possibilities, none of them completely satisfying. One idea is that the star is creating technetium on its surface through some unknown nuclear process. Maybe there's a mechanism we don't understand that can produce these elements in the star's atmosphere, but this seems unlikely. We have a pretty good understanding of nuclear physics, and there's no known process that could do this in the cool outer layers of a star. Another idea is that the technetium is being brought up from the star's interior. Maybe deep inside the star, nuclear reactions are creating technetium and convection currents are carrying it to the surface. But again, this doesn't quite work. The star's interior isn't hot enough to create technetium through normal nuclear reactions. A third idea, which sounds like science fiction, is that the star contains super heavy elements with atomic numbers far beyond anything we've seen. In theoretical nuclear physics, there's something called the island of stability. The idea is that if you go far enough up the periodic table, beyond the known elements, you might find a region where certain super heavy elements are relatively stable. Some of these super heavy elements, if they exist, might decay into technetium or promethium as intermediate products. So the star might contain super heavy elements that are slowly decaying, replenishing the supply of technetium and promethium. This is highly speculative. We've never observed super heavy elements in nature. We've created a few in particle accelerators, but they decay almost instantly. The island of stability is a theoretical prediction, not an established fact. Still, Przybylski's star is so weird that astronomers are willing to consider exotic explanations. Another strange thing about the star is its composition. It has unusually high amounts of certain rare earth elements. Its spectrum shows strong lines of elements like holmium, dysprosium, and europium. These elements are much more abundant in Przybylski's star than in the Sunday. It's what's called a chemically peculiar star. There are several types of chemically peculiar stars, and they're thought to arise because of atmospheric processes that concentrate certain elements. Radiation pressure and magnetic fields can cause some elements to sink or float in the star's atmosphere, creating unusual abundances. But even among chemically peculiar stars, Przybylski's star is exceptional. Its abundance patterns are more extreme than almost any other star, and the presence of short-lived radioactive elements is unique. Some astronomers have wondered if Przybylski's star might have a companion. Maybe it's in a binary system with a neutron star or white dwarf, and material from the companion is falling onto Przybylski's star, bringing radioactive elements with it. But we see no evidence of a companion. The star's motion doesn't show the wobble we'd expect from an orbiting partner. As of 2025, Przybylski's star remains a mystery. For more than 60 years, astronomers have been observing it. And for more than 60 years, it's shown technetium and promethium in its spectrum. These elements should have decayed away long ago, yet they're still there. Either there's a nuclear process we don't understand, or the star contains exotic matter, or there's something fundamentally wrong with our observations or interpretations. None of these options is particularly satisfying, which is why Przybylski's star is one of the strangest objects in the sky. On October 19, 2017, astronomers at the Pan-STARRS telescope in Hawaii detected something moving through the solar system. At first, they thought it was a comet or asteroid, but as they gathered more data, they realized this object was different. Very different. They named it Oumuamua, a Hawaiian word meaning scout or messenger, and it was the first confirmed interstellar object to pass through our solar system. Oumuamua came from outside the solar system, from interstellar space. It approached from the direction of the constellation Lyra, passed through the inner solar system, and was headed back out into interstellar space. We only had a few weeks to study it before it became too faint and distant to observe. What we learned during those weeks was fascinating and confusing. Oumuamua was strange, really strange. First, its shape. Based on how its brightness varied as it tumbled through space, astronomers calculated that Oumuamua was extremely elongated. The best estimates suggested it was about 400 meters long and only about 40 meters wide. That's a ratio of 10 to 1. It's cigar-shaped, or maybe more like a pancake, depending on the exact geometry. This is unusual. Most asteroids and comets are more spherical or irregular, not long and thin. An elongated shape like Oumuamua's is possible but rare. Second, its surface. Oumuamua was reddish in color, similar to some objects in the outer solar system. This suggested its surface had been exposed to cosmic rays for a long time, which can redden the surface material. So far, that's normal. But Oumuamua showed no signs of a coma. Comets, when they get close to the sun, heat up. Ice on their surface vaporizes, creating a cloud of gas and dust called a coma. It's the coma that gives comets their characteristic appearance. Oumuamua didn't have a coma. Even when it passed close to the sun, well inside Mercury's orbit, no coma appeared. This suggested it wasn't a comet, at least not a typical icy comet. Maybe it was more like an asteroid, made of rock or metal. But then came the really weird part. Oumuamua's trajectory didn't match what we expected. After it passed the sun and was heading back out of the solar system, it was accelerating slightly more than it should have. When you calculate an object's trajectory, you account for the gravitational pull of the sun and planets. Those forces are predictable. Based on gravity alone, we could predict exactly where Oumuamua should be at any given time. But it was moving slightly faster than expected. It was being pushed by something other than gravity. This is normal for comets. The evaporating gas from a comet's coma creates a rocket effect, pushing the comet slightly. This non-gravitational acceleration is well understood for comets. But Oumuamua didn't have a coma. So what was pushing it? Scientists proposed several ideas. Maybe Oumuamua was outgassing, but the gas was not carrying enough dust to create a visible coma. Maybe it was venting gas from one side, creating thrust, but we just couldn't see it. Some observations suggested there might be very faint traces of gas, but it's hard to be sure. Another idea was that Oumuamua was being pushed by sunlight. All objects in the solar system experience radiation pressure from the Sunday photons from the sun, hit the object, and transfer momentum, pushing it slightly. For most objects, this force is tiny, much smaller than gravity. But if an object is very thin and light, like a sheet or sail, radiation pressure can be significant. Maybe Oumuamua was very thin. Maybe it was more like a pancake than a cigar. If it was only a few meters thick but hundreds of meters across, and if it was made of relatively light material, radiation pressure could explain the observed acceleration. But this raises questions. How would such an object form naturally? Why would it be so thin? It's hard to imagine natural processes creating a thin, rigid sheet of rock or ice hundreds of meters across. This is where things get really speculative. In 2018, two Harvard astronomers, Abraham Loeb and Shmuel Bialy, published a paper suggesting that Oumuamua might be artificial. Specifically, they suggested it could be a light sail, a thin reflective sheet designed to be pushed by starlight. Such a sail could be a spacecraft or a probe sent by an alien civilization. This suggestion generated a lot of controversy. Most scientists were skeptical. The alien hypothesis is always the last resort in astronomy. You only invoke aliens when you've exhausted all natural explanations. And there were natural explanations for Oumuamua, even if they were a bit strained. Loeb argued that we should at least consider the possibility. If Oumuamua was artificial, it would be the most important discovery in human history. The fact that it's unlikely doesn't mean we should dismiss it without consideration. But most astronomers think Oumuamua is natural. Probably a comet with unusual properties, or an asteroid with a weird shape, or maybe a piece of a shattered planet from another star system. These explanations require fewer assumptions than aliens. The problem is, we'll never know for sure. Oumuamua is gone. It's too far away and too faint to observe now. We had a few weeks to study it, and we didn't get all the data we wanted. If another interstellar object passes through the solar system, we'll be better prepared. We'll have more telescopes ready to observe it. We'll get more detailed data. In fact, a second interstellar object was discovered in 2019. It's called Borisov, and it's definitely a comet. It has a coma and a tail, and behaves exactly like comets in our solar system do. Borisov is unremarkable, which makes it remarkable. It shows that interstellar comets are pretty much like solar system comets. But Oumuamua remains unique. We've never seen another object quite like it. Maybe it was just a weird natural object. Maybe it was something more. We'll probably never know. What's clear is that interstellar objects pass through our solar system occasionally. The galaxy is full of asteroids and comets that have been ejected from their home star systems. They drift through interstellar space. Some of them, by chance, pass through our solar system. We can detect them now, and every one we detect teaches us something new about the universe beyond our Sunday. In June of 2018, telescopes around the world detected a bright explosion in a galaxy 200 million light-years away. They labeled it AT2018 Cow. The name comes from the automated naming system for astronomical transients. The cow part is just random letters, but it's become the nickname for this event. At first, astronomers thought it was a supernova. Supernovae are exploding stars, and they happen regularly. We detect dozens of them every year. But as they gathered more data, they realized AT2018 Cow was different. Very different. First, it was extremely bright. About 10 to 100 times brighter than a typical supernova. And it got bright fast. Most supernovae take weeks to reach peak brightness. AT2018 Cow reached peak brightness in just a few days. Then it faded quickly. Most supernovae remain visible for months, gradually fading over time. AT2018 Cow faded in weeks. It was like someone turned on a cosmic flashlight, shined it for a brief moment, and turned it off again. The light spectrum was also unusual. It didn't match the spectra of known types of supernovae. The temperatures were extremely high, tens of thousands of degrees. And the explosion seemed to be expanding very fast, at a significant fraction of the speed of light. Astronomers were baffled. What kind of explosion could be this bright, this fast, this hot, and this different from anything they'd seen before? They quickly realized AT2018 Cow wasn't alone. As they looked through archival data and continued monitoring the sky, they found more events like it. These ultra-fast, ultra-bright transients seem to be a whole new class of astronomical event. They're sometimes called fast blue optical transients, or FBOTs. The name describes them well. They're fast peaking and fading in days or weeks. They're blue, emitting lots of ultraviolet light, which indicates high temperatures. And they're optical transients, meaning they appear and disappear in visible light. As of 2025, we've found a handful of these events. Not many, maybe a few dozen. They're rare, or at least rarely detected. and we still don't fully understand what causes them. Several theories have been proposed. One idea is that they're the birth of black holes or neutron stars. When a massive star dies, its core collapses. If the core is heavy enough, it forms a black hole. If it's lighter, it forms a neutron star. This collapse releases an enormous amount of energy. Normally, most of this energy goes into blowing apart the outer layers of the star, creating a supernova. But in some cases, maybe the energy is released differently. Maybe it creates a jet that punches through the star's outer layers and shoots out into space. This jet would create a bright, fast transient that looks different from a normal supernova. Another idea is that F-bots are the result of a star being torn apart by a black hole. This process is called tidal disruption. If a star wanders too close to a black hole, the black hole's gravity rips the star apart. The stellar material spirals into the black hole, heating up and emitting enormous amounts of energy. Tidal disruption events are known to occur, and they can be very bright. But most tidal disruption events are slower than F-bots. They take months to peak and fade. F-bots are much faster. Maybe FBOTs are a special type of tidal disruption where a small black hole disrupts a white dwarf or neutron star. The dynamics would be different, potentially explaining the speed and brightness. A third idea involves interactions between two compact objects. Maybe a white dwarf collides with another white dwarf or a neutron star. The collision would release enormous energy in a brief burst, creating an F-bot. The truth is, we don't know. FBOTs are so new that we're still figuring out their basic properties. Every new detection gives us more data, helping us narrow down the possibilities. What's exciting about FBOTs is that they represent something genuinely new. Astronomy has been studying supernovae for centuries. We've developed detailed models of how different types of supernovae work. We thought we understood exploding stars pretty well. Then, along comes AT 2018 Cow, and it breaks all the rules. It's brighter, faster, and different from anything we expected. It forced astronomers to realize there are types of cosmic explosions they hadn't anticipated. This happens sometimes in science. You think you understand something, and then nature throws you a curveball. You detect something that doesn't fit your models. That's when science gets really interesting, because it means there's something new to learn. As telescopes get better, and we monitor more of the sky more often, we'll probably detect more F-bots. Each one gives us clues. Over time, we'll figure out what's causing them. But right now, in 2025, they remain one of the strange, unexplained phenomena in the universe. Let me tell you about a star that shouldn't exist. Its official name is HD 140283, but astronomers call it the Methuselah star, named after the biblical figure who supposedly lived to be 969 years old. The Methuselah star is about 190 light-years away from Earth. It's visible with binoculars, if you know where to look, in the constellation Libra. It's an old star, a subgiant, meaning it's exhausted the hydrogen in its core and is starting to evolve off the main sequence. Stars like this are ancient. They formed in the early universe, when conditions were different from today. By studying them, we can learn about the universe's history. Astronomers can estimate a star's age using several methods. One method looks at the star's composition. The universe started with almost pure hydrogen and helium. Over time, stars have created heavier elements through nuclear fusion and supernova explosions. These heavy elements, which astronomers call metals, accumulate over time. So a star with very few metals probably formed early, before many generations of stars had enriched the interstellar medium with heavy elements. The Methuselah star has very low metallicity. It contains about 250 times less iron than the Sunday. This suggests it formed early, when the universe was young and heavy elements were rare. Another method to estimate age looks at the star's nuclear fuel consumption. Stars fuse hydrogen into helium in their cores. Once they run out of hydrogen, they start fusing helium into heavier elements. The rate of these reactions depends on the star's mass and composition. By observing a star's properties, temperature, luminosity, composition, you can estimate how long it's been burning and therefore how old it is. When astronomers applied these methods to the Methuselah star, they got an uncomfortable result. The star's age came out to around 14 billion years, with error bars that uncomfortably overlap with the age of the universe itself. Here's the problem. The universe itself is only about 13.8 billion years old. We know this from multiple independent measurements. The cosmic microwave background, the expansion rate of the universe, the ages of the oldest star clusters, they all point to an age of about 13.8 billion years. So how can a star be around 14 billion years old in a 13.8 billion year old universe? The error bars technically allow for ages just barely younger than the universe, but it's cutting it extremely close. That's uncomfortably tight. Initially, when this result came out, some people suggested maybe our measurement of the universe's age was wrong. Maybe the universe is older than we thought. But as measurements improved, the universe's age became more certain. It's definitely around 13.8 billion years, with very small error bars. So the problem must be with the star's age estimate. But how could we be wrong? The methods for estimating stellar ages are well established. They're based on solid physics. The key is the error bars. The Methuselah star's age is around 14 billion years, with uncertainties that technically allow for it to be as young as 13.7 or 13.8 billion years. That's just barely younger than the universe, cutting it incredibly close, but it's technically possible. If the star formed very soon after the Big Bang, within the first few 100 million years, it could be that old. But even this is uncomfortable. The very first stars in the universe were different from stars today. They formed from pure hydrogen and helium, with no heavy elements. These first stars were probably very massive and short-lived. The Methuselah star doesn't fit the profile of a first-generation star. Second-generation stars, which formed from gas enriched by the first supernovae, would have some heavy elements. The Methuselah star has a small amount of heavy elements, consistent with being a second-generation star. But second-generation stars wouldn't have formed immediately after the Big Bang. It would take time for the first stars to live, die, and enrich the interstellar medium. Maybe a few 100 million years. So the Methuselah star probably formed at least a few 100 million years after the Big Bang. That would make its maximum possible age about 13.5 billion years or less. The problem is, the observations keep suggesting it's older than that. Even with improved measurements and refined models, the star's age estimate stays around 14 billion years. The error bars have gotten smaller over time, which is the opposite of what we'd hope. We'd like the error bars to encompass a younger age that's comfortable. So what's going on? There are a few possibilities. One is that our models of stellar evolution are wrong in some subtle way. Maybe low metallicity stars evolve differently than we think. Maybe there's a process we don't understand that affects their nuclear burning rates. Another possibility is that our distance measurement to the star is wrong. Age estimates depend on knowing the star's luminosity, and luminosity estimates depend on knowing the distance. If the star is closer or farther than we think, its age estimate would change. Astronomers have measured the distance to the Methuselah star using parallax. As Earth orbits the Sun, nearby stars appear to shift position against the background of more distant stars. By measuring this shift, you can calculate the distance. The Gaia satellite has measured parallaxes for billions of stars with unprecedented precision, including the Methuselah star. But there's still some uncertainty. Maybe the distance is slightly different than we think, enough to bring the age estimate down to something more comfortable. A third possibility is that the star is simply younger than the best estimates suggest, and we're just on the unlucky end of the statistical distribution. When you measure something with uncertainty, sometimes the true value is at the edge of the error bars. Maybe the Methuselah star is really 13.5 billion years old, and the 14.5 billion year estimate is just a statistical fluctuation. As of 2025, the Methuselah star remains uncomfortably old. Astronomers keep refining the measurements, hoping to resolve the tension. But for now, it stands as one of the strange things in the universe. A star that, according to our best measurements, seems to be older than the universe itself. Of course, it can't actually be older. Something about our measurements or models must be off, but figuring out what is taking time, and until we do, the Methuselah star will continue to puzzle astronomers. Now, here's something interesting to think about. All of these strange discoveries might seem unrelated. A radio signal from the 1970s, a star that dims irregularly, giant radio circles, structures that are too large, empty voids, cold spots in ancient light, radioactive elements in a star, an interstellar visitor, weird explosions, an impossibly old star. They seem like completely separate mysteries. But maybe they're not. Maybe they're all telling us the same thing. That the universe is more complex than our current models suggest. That there are processes, phenomena, or physics we don't fully understand yet. Think about it. The WOW signal tells us there are radio sources we haven't identified. Tabby's star tells us stars can behave in unexpected ways. Odd radio circles tell us galaxies can create structures we're only beginning to see. The giant arc and big ring tell us the universe might not be as uniform as we thought. The Boötes void tells us emptiness can be more extreme than our models predict. Each mystery on its own is just an oddity, something strange we need to explain, but taken together they paint a picture of a universe that's still surprising us, still showing us things we didn't expect. This is actually normal in the history of science. When you're on the edge of understanding something new, you start seeing anomalies, things that don't quite fit. At first, they seem like isolated problems. But eventually, someone connects the dots. Someone realizes these anomalies are all symptoms of something bigger, something we haven't understood yet. That's how we discovered relativity. In the late 1800s, there were several problems in physics. The orbit of Mercury didn't quite match predictions. The speed of light seemed to be constant, regardless of how you measured it. These seemed like separate issues. Then Einstein came along and showed they were both explained by the same new theory. Relativity connected the dots. Maybe that's what's happening now with these cosmic mysteries. Maybe they're all pieces of a puzzle. And someday, someone will figure out how they fit together. They'll develop a new theory or discover a new phenomenon that explains all of them at once. Or maybe not. Maybe each mystery has its own separate explanation. Maybe the WOW signal was a comet. Maybe Tabby's star has a dust cloud. Maybe odd radio circles are shock waves. Maybe the giant arc is just chance. Maybe Przybylski's star has some unknown nuclear process. We won't know until we figure them out. But the possibility that they're connected, that they're all telling us something fundamental about the universe, that's exciting. That's what makes this such a fascinating time to be studying astronomy. Let me tell you something that might surprise you. Some of the greatest advances in astronomy came from being wrong, from making observations that contradicted what we thought we knew. In the early 1900s, astronomers observed distant galaxies and noticed they were moving away from us. The farther away they were, the faster they were receding. This didn't make sense. Why would everything be moving away from us? Are we at the center of the universe? But as they thought about it more, they realized this pattern would happen if the universe itself was expanding. If space itself was stretching, then galaxies would move apart, and the ones that are farther away would appear to move faster. This observation led to the Big Bang theory. The entire universe started from a single point and has been expanding ever since. Nobody expected that. It contradicted the prevailing view that the universe was static and unchanging. But the observations forced astronomers to change their minds. And that unexpected observation became the foundation of modern cosmology. In the 1960s, astronomers discovered quasars. These were points of light that looked like stars but had strange properties. They were incredibly bright, brighter than entire galaxies, and they were very far away, billions of light years distant. Nothing we knew about stars could explain how they could be so bright. Eventually, scientists realized quasars weren't stars at all. They were the centers of galaxies containing supermassive black holes. Matter falling into these black holes released enormous amounts of energy, creating the brightest sustained sources of light in the universe. This discovery changed how we thought about galaxies. We realized that most large galaxies have supermassive black holes at their centers. These black holes play a crucial role in galaxy evolution. None of this was known before quasars forced us to reconsider what was possible. In the 1980s, astronomers measuring the expansion of the universe expected to find that it was slowing down. Gravity from all the matter in the universe should be pulling everything back together, slowing the expansion. But when they made careful measurements using distant supernovae, they found the opposite. The expansion was accelerating. This made no sense. What could be pushing the universe apart? This observation led to the concept of dark energy, a mysterious force that makes up about 68% of the universe's total energy. We still don't really know what dark energy is, but we know it exists because the observations demand it. Each of these discoveries started with an observation that didn't make sense, something that contradicted expectations. And each time, instead of ignoring the observation or assuming it was wrong, astronomers followed where the evidence led. They changed their theories to match reality. That's what's happening now with the mysteries I've described. We have observations that don't fit our current understanding. We could ignore them. We could assume they're measurement errors or statistical flukes. But that's not how science works. Instead, we take them seriously. We study them carefully. We try to understand them. And maybe, just maybe, they'll lead to the next big breakthrough in our understanding of the universe. The reason we're finding so many strange things in space right now isn't because the universe suddenly got stranger. It's because our tools got better. We can see things we couldn't see before. We can measure things we couldn't measure before. Think about the WOW signal. It was detected by a radio telescope in 1977. That telescope, the Big Ear, was relatively simple by today's standards. It could detect strong radio signals, but it couldn't pinpoint their exact location very well. It couldn't analyze the signals in great detail. Today, we have much better radio telescopes. The Very Large Array in New Mexico, the ALMA array in Chile, the upcoming Square Kilometer Array, which will be the most sensitive radio telescope ever built. These instruments can detect much fainter signals. They can locate sources precisely. They can analyze signals in incredible detail. If the WOW signal happened today, we'd learn so much more about it. We'd know exactly where it came from. We'd know its properties much more precisely. We might even be able to figure out what caused it. The same is true for all these mysteries. We're finding them because we have better tools. And as our tools continue to improve, we'll find more. We'll also understand the ones we've already found much better. Tabby's star was discovered by the Kepler Space Telescope, which launched in 2009. Kepler was designed to find exoplanets by watching for the tiny dips in starlight when planets pass in front of their stars. It monitored more than 150,000 stars continuously for several years. Before Kepler, we couldn't do this kind of monitoring. We had to observe each star individually, and we couldn't watch them continuously. Tabby's star's weird dimming pattern would have been nearly impossible to detect. But Kepler gave us continuous data on thousands of stars, and that's how we found Tabby's star. We weren't looking for it. We were looking for planets. But Kepler's ability to monitor stars continuously revealed something nobody expected. Now we have TESS, the Transiting Exoplanet Survey Satellite, which is doing similar work. We have the James Webb Space Telescope, which can observe in infrared light with incredible sensitivity. We have ground-based telescopes with adaptive optics that can see almost as clearly as space telescopes. Each of these instruments can discover unexpected things. Each one gives us a new way of looking at the universe. And the more ways we look, the more strange things we find. In the coming years, we'll have even better tools. The extremely large telescope is being built in Chile. When complete, it will have a mirror 39 meters across. That's enormous. It will be able to see incredibly faint and distant objects. It will be able to analyze the atmospheres of exoplanets, looking for signs of life. The square-kilometer array, when complete, will have a collecting area of 1 square kilometer. That's about 250 acres of radio receivers. It will be 50 times more sensitive than any current radio telescope. If there are radio signals out there like the WOW signal, the square-kilometer array will find them. NASA is planning new space telescopes. Some will look for signs of life on exoplanets. Some will study the early universe. Some will map out dark matter. Each will have the potential to discover something unexpected. And here's the thing. Every time we build a better telescope, we find surprises. Every single time. There's never been a case where we built a more sensitive instrument and found exactly what we expected and nothing more. The universe always surprises us. So we can be pretty confident that in the coming decades, we'll discover more strange things, more mysteries to puzzle over, more observations that don't quite fit our theories. And that's exciting, because mysteries drive progress. They force us to think harder, to question our assumptions, to develop new ideas. Let me tell you something about the people who study these mysteries. They're not some distant group of super-intelligent beings who have everything figured out. They're regular people. People who get excited when they find something weird. People who stay up late trying to understand confusing data. People who argue with each other about what observations mean. When Jerry Eman saw the WOW signal in 1977, he was reviewing paper printouts of data. The Big Ear telescope recorded data on paper, numbers indicating signal strength. Most of the time, the numbers were low, background noise. But on this particular printout, there was a sequence of numbers that was clearly different, much higher than background. Eamon grabbed a red pen and circled the sequence. Next to it, he wrote, "Wow." He was genuinely surprised and excited. That's how the signal got its name. It wasn't some official designation. It was one person's spontaneous reaction to seeing something unexpected. That human reaction, that sense of wonder and surprise, is still part of astronomy today. When Tabby's star was discovered, the astronomers studying it were genuinely puzzled. They knew they were seeing something unusual. They worked hard to try to explain it. When conventional explanations didn't work, they had to consider unconventional ones, including the possibility of an alien megastructure. That suggestion was controversial. Many scientists criticized it. They thought it was irresponsible to mention aliens when there were potential natural explanations. But the scientists who proposed it weren't saying it definitely was aliens. They were saying they couldn't rule it out. And that's honest. When you have an observation you can't explain, you have to consider all possibilities, even the unlikely ones. This is what science looks like from the inside. It's not a smooth process where everyone agrees and everything makes sense. It's messy. People disagree. They debate. They argue about interpretations. They propose ideas that turn out to be wrong. But through all this mess, progress happens. Someone makes an observation, others try to confirm it. People propose explanations. They test those explanations. Some explanations get ruled out. New observations are made. Gradually, understanding emerges. The scientists studying Przybylski's star have been puzzled for decades. They've proposed many explanations for the radioactive elements in its atmosphere. None of them quite work, but they keep trying. They keep making observations. They keep refining their ideas. That persistence is what drives science forward. Not giving up when things are confusing. Keeping at it. Trusting that eventually, with enough work, understanding will emerge. And sometimes, it takes a long time. The cosmic microwave background was discovered in 1964, but it took decades of observations and analysis before scientists really understood what they were seeing. The detailed maps we have now, showing the tiny temperature variations, came from satellites launched in the 1990s and 2000s. The CMB cold spot was noticed in the early 2000s. It's now 20, 25. We've been studying it for more than 20 years. We still don't fully understand it, but we're not giving up. We keep observing. We keep thinking. We keep trying to figure it out. That's what science requires. Patience, persistence, willingness to live with uncertainty. These aren't easy things. It's much more comfortable to have answers than questions. But the universe doesn't care about our comfort. It is what it is. Our job is to figure it out. You might wonder why some of these mysteries have been around for years or even decades without being solved. The WOW signal was in 1977. That's almost 50 years ago. Why haven't we figured it out yet? There are several reasons. First, in many cases, we simply don't have enough data. The WOW signal lasted 72 seconds. We have one data point, one observation. It never repeated. That makes it incredibly difficult to study. Imagine trying to understand what an animal is based on seeing it once for 72 seconds. You might get some information. You could see its color, roughly its size, maybe how it moves, but you couldn't study its behavior. You couldn't see what it eats, or where it lives, or how it reproduces. One brief observation is limiting. That's the situation with the WOW signal. We have one observation. We can analyze it in detail, and scientists have done that. But there's only so much you can learn from a single data point. We need more observations, and so far, we haven't gotten them. Tabby's star is a different situation. We have lots of data on it. We've been observing it continuously since it was discovered. We've watched it dim multiple times. We have observations from multiple telescopes in different wavelengths of light. But even with all that data, we're still not certain what's causing the dimming. The problem here isn't lack of data. It's that the phenomenon is complex. Multiple things might be happening. The dust theory explains some observations, but not all of them. We might need more detailed models, or more observations in specific wavelengths, or better theoretical understanding of how dust behaves around stars. For the Methuselah star, the problem is measurement precision. We can measure the star's properties, its temperature, brightness, composition very accurately. We can measure its distance reasonably well. But when we use all this data to estimate the star's age, we get a result that doesn't make sense. The issue is that our age estimate depends on multiple measurements, and each has some uncertainty. When you combine multiple uncertain measurements, the uncertainties add up. Maybe one of our measurements is slightly off. Maybe our models of how stars evolve have a small error. These small errors could add up to make our age estimate too high. But figuring out which measurement is wrong, or where our models need improvement, is difficult. It requires very precise observations and very detailed models, and that takes time. Some mysteries take long to solve, simply because they require technology we don't have yet. Before we had space telescopes, we couldn't observe many things clearly. Earth's atmosphere blocks certain wavelengths of light and distorts others. Space telescopes solved that problem. But space telescopes are expensive and take years to build. The James Webb Space Telescope was first proposed in the 1990s. It launched in 2021. That's decades from concept to reality. So if solving a mystery requires a specific type of observation that only a new telescope can make, we might have to wait decades for that telescope to be built. Other mysteries take long because they require a theoretical breakthrough. Sometimes we have all the data we need, but we don't have the right conceptual framework to understand it. We need someone to think of a new idea, a new way of looking at the problem. These theoretical breakthroughs are unpredictable. They happen when someone has a creative insight. You can't schedule creativity. You can't say we'll have a breakthrough on Tuesday. It happens when it happens. The discovery of dark energy is a good example. In the 1990s, astronomers measured distant supernovae to determine how fast the universe's expansion was slowing down. But they found the expansion was speeding up. This made no sense based on existing theory. It took time for the astronomical community to accept this result. Many scientists initially thought there must be an error in the measurements. But as more data came in from independent teams, it became clear the result was real. The expansion really was accelerating. But what could cause this? There was no explanation in existing physics. Scientists had to propose something new. They called it dark energy. They still don't know what it is, but at least now they have a name for it and can study it. That process took years. From the first confusing observations to the acceptance that something new was needed to the proposal of dark energy. Each step took time as scientists gathered more data, debated interpretations, and developed new theoretical frameworks. The mysteries I've described tonight are in various stages of this process. Some, like the WOW signal, are still waiting for more data. Some, like Tabby's star, have lots of data but need better theoretical understanding. Some, like the Methuselah star, need more precise measurements. Some, like the CMB cold spot, might need entirely new theoretical ideas, but all of them are being worked on. Scientists are observing, measuring, thinking, debating. Progress is happening, even if it's slow, and eventually these mysteries will be solved. Maybe not all of them in our lifetime, But someday, these strange discoveries teach us something important about how science works. Science isn't about having all the answers. It's about honestly confronting what we don't know. When we discover something we can't explain, the scientific response isn't to make up a story or ignore it. The response is to admit we don't know, to study it carefully, to consider multiple explanations, to gather more data, to think creatively about possible solutions. This is very different from other ways of knowing. In some belief systems, admitting you don't know something is seen as weakness. There's pressure to have answers, even if those answers aren't well supported. Science takes the opposite approach. Admitting you don't know is honest. It's the first step toward knowing. You can't solve a problem if you pretend it doesn't exist, or if you accept a convenient answer without evidence. The wow signal is a perfect example. We don't know what it was. Scientists have been honest about that for almost 50 years. They've proposed various possibilities: natural radio sources, alien signals, terrestrial interference. But they admit none of these explanations is completely satisfying. That honesty is valuable. It means when we finally do figure out what the wow signal was, we'll know the explanation is based on solid evidence, not wishful thinking. The same is true for all these mysteries. Scientists are being honest about what they don't understand. That honesty is a strength, not a weakness. This approach also means science is self-correcting. When we make a mistake, when a theory turns out to be wrong, we change it. We update our understanding based on new evidence. History is full of examples. Scientists used to think the Earth was the center of the universe. Observations proved otherwise. Scientists used to think the universe was static. Observations showed it was expanding. Scientists used to think nothing could escape a black hole. Theoretical work by Stephen Hawking showed that black holes can evaporate through a quantum process. Each time, the scientific community changed its views based on evidence. That's how it should work. Our understanding should evolve as we learn more. The mysteries I've described will likely lead to changes in our understanding. Maybe small changes, maybe large ones. But whatever we learn from them will make our picture of the universe more accurate. That's the goal. Not to protect cherished theories, not to cling to ideas because they're comfortable or familiar, but to understand reality as it actually is, even when reality is strange, even when it contradicts our expectations. There's another important lesson from these mysteries. Technology matters. The tools we use to observe the universe determine what we can discover. The wow signal was detected because we built radio telescopes. Before radio astronomy existed, we had no way to detect signals like that. The whole phenomenon of cosmic radio sources was unknown until the mid-20th century. Tabby star was discovered because we built the Kepler Space Telescope specifically to monitor thousands of stars continuously. That capability didn't exist before. We couldn't keep track of that many stars at once. Kepler changed that. Odd radio circles were discovered because we built ASCAP, a new type of radio telescope in Australia. ASCAP can survey large areas of the sky quickly in radio wavelengths. It found these circles that previous telescopes had missed, not because they weren't there, but because previous telescopes couldn't see them well. The cosmic microwave background was discovered by accident in 1964 when engineers were testing a new sensitive radio antenna. They found a persistent background noise coming from all directions. At first, they thought it was a problem with their equipment. Eventually, they realized they were detecting the afterglow of the Big Bang. But they needed that sensitive antenna to detect it. Each advance in technology opens new windows. Each new instrument reveals things that were hidden before. And we can be confident that future instruments will reveal things we haven't imagined yet. This is why funding for scientific instruments is so important. It's not just about satisfying curiosity, though that's valuable too. It's about expanding human knowledge, about discovering new phenomena that might have practical applications someday. Many technologies we use every day came from astronomy research. The sensors in digital cameras were developed for space telescopes. Wireless internet technology came from research on radio astronomy. Medical imaging techniques like CT scans use principles developed in X-ray astronomy. When we build new telescopes, we're not just learning about distant stars and galaxies. We're developing new technologies that often find uses in everyday life. The mysteries we discover with these telescopes drive further innovation as we try to solve them. So investing in astronomy isn't just about satisfying our curiosity about the universe, though that alone would be worthwhile. It's also an investment in technology and innovation that benefits everyone. There's something fascinating about how humans respond to mysteries. We're pattern-seeking creatures. Our brains are wired to look for explanations. When we encounter something we can't explain, it bothers us. It nags at us. We want to figure it out. That's why these cosmic mysteries are so compelling. They're real things that exist, that we've observed and measured, but we can't explain them. That creates a kind of mental itch that we want to scratch. Think about the wow signal. For almost 50 years, people have been thinking about it. What was it? Where did it come from? Was it natural or artificial? These questions don't have clear answers, and that bothers us. We want to know, but here's something interesting. Living with uncertainty, with not knowing, is actually valuable. It keeps us humble. It reminds us that we don't have everything figured out. It prevents us from becoming too confident in our current understanding. Throughout history, humans have often been too confident. We thought we understood how the world worked, only to discover we were wrong. We thought the Earth was flat. We thought it was the center of the universe. We thought continents didn't move. We thought atoms were the smallest things. We were wrong about all of these. Mysteries like the ones I've described tonight remind us that we might still be wrong about important things. Our current understanding of the universe might be incomplete. There might be major phenomena or principles we haven't discovered yet. That's not a bad thing. It's actually exciting. It means there's still so much to learn. The universe still has secrets to reveal. We're not at the end of discovery. We're somewhere in the middle, maybe even just at the beginning. When you think about it that way, mysteries aren't problems to be frustrated about. They're invitations. Invitations to explore, to discover, to learn. Each mystery is pointing us towards something we don't know yet. Something that, once we understand it, will expand our view of the cosmos. So, we've talked about a radio signal that appeared once and never again. A star that dims in ways no other star does. Giant radio circles around galaxies that we can't explain. Structures in the universe that are too large to exist according to theory. A void that's almost empty when it should be full of galaxies. A cold spot in the cosmic microwave background that's too cold to be a coincidence. A star with radioactive elements that should have decayed billions of years ago. An interstellar visitor with weird properties. Explosions that are brighter and faster than any known type of supernova. And a star that might be older than the universe. These are just some of the strange things we've discovered in space. And here's what's remarkable about them. They're all real. These aren't theories or speculation. These are actual observations, things we've seen and measured. But more than that, they're all invitations. Invitations to understand the universe better. invitations to think more carefully, observe more precisely, and imagine new possibilities. Each mystery is the universe's way of telling us we don't know everything yet, and that's valuable. Science is about trying to explain observations. When we see something, we come up with hypotheses. We test those hypotheses, we build models, we make predictions, and when our predictions match observations, we feel confident that we understand what's going on. But sometimes, observations don't match our predictions. Sometimes we see things we can't explain. That's when science gets really interesting. Every mystery I've described tonight is an opportunity. It's a chance to learn something new. Maybe our models are incomplete. Maybe there are processes in the universe we haven't discovered yet. Maybe physics works differently than we thought in certain situations. History shows that when observations don't match theory, it's usually the theory that needs updating. That's how science progresses. Newton's laws of motion worked great until we measured things moving close to the speed of light. Then we needed Einstein's relativity. Relativity works great until you get down to quantum scales. Then you need quantum mechanics. None of this means science is wrong. It means science is constantly refining itself. We're always improving our understanding, and every mystery is a clue pointing towards something we don't know yet. The wow signal might teach us about natural radio sources we haven't encountered, or it might be evidence of something even more profound. Either way, it's a data point. Tabby's star is teaching us that stars can behave in ways we didn't anticipate. Whatever is dimming that star, natural or otherwise, it's expanding our understanding of what's possible. Odd radio circles are revealing structures in the universe we weren't aware of. They're showing us that galaxies can create or be associated with features that we're only now learning to see. The giant arc and big ring are challenging our assumptions about how uniform the universe is. They're suggesting that at the largest scales, things might be more complex than our models predicted. The Boötes void and the CMB cold spot are probing the limits of structure formation. They're testing whether our understanding of gravity in the early universe is complete. Przybylski's star is hinting that nuclear physics in stellar atmospheres might be more complex than we thought. Or maybe it's teaching us about exotic matter. Oumuamua opened our eyes to the fact that interstellar objects pass through our solar system. We're now watching for more. Each one will tell us about planetary systems around other stars. Fast blue optical transients are showing us that stellar death comes in more varieties than we knew. They're expanding the catalogue of cosmic explosions. And the Methuselah star is reminding us that our measurements and models always have uncertainties. It's keeping us humble. Here's something to think about. We've been seriously studying the universe for maybe 400 years. Galileo pointed his telescope at the sky in 1609. That's when modern astronomy really began. 4 centuries. The universe is 13.8 billion years old. 400 years is nothing. It's 0.00003% of the universe's age. We've been looking at the cosmos for the tiniest fraction of its existence. And during that tiny fraction of time, we've discovered an enormous amount. We've figured out what stars are, how they work, how they're born and die. We've discovered other galaxies. We've learned the universe is expanding. We've detected gravitational waves, black holes, neutron stars. We've found thousands of exoplanets. We've mapped the cosmic web. We've observed the cosmic microwave background. All of this in just 4 centuries. Imagine what we'll discover in the next 4 centuries, or the next 4,000 years, or the next 4 million. The universe is full of secrets. Some we've uncovered. Many more remain hidden. Every telescope we build reveals new mysteries. Every new wavelength we observe shows us structures we didn't know existed. Radio astronomy began in the 1930s. Before that, we had no idea the universe was full of radio sources. We couldn't see pulsars, quasars, or the cosmic microwave background. We didn't know about odd radio circles because we couldn't see them. X-ray astronomy began in the 1960s. Infrared astronomy, gamma-ray astronomy, gravitational wave astronomy. Each opened new windows on the universe. Each revealed phenomena we hadn't imagined. What will we discover with the next generation of telescopes? What wavelengths haven't we observed yet? What techniques haven't we developed? I guarantee that in 50 years, we'll know about things that would sound like science fiction today. We'll have detected phenomena that we can't even conceive of right now. The universe is stranger than we know. It's probably stranger than we can know, given our current level of technology and understanding. You might be wondering why any of this matters. Why should you care about strange radio signals or weird stars or giant structures in the distant universe? These things don't affect your daily life. You still have to go to work, pay bills, deal with everyday problems. But I think understanding the universe matters for a deeper reason. It tells us about our place in existence. It gives us perspective. We're living on a planet, orbiting an ordinary star in an ordinary galaxy. We're part of a universe that's vast and old and full of wonders. Some of those wonders we understand, many we don't. Knowing this changes how you see things. The problems that seem overwhelming, the disagreements that feel so important, they're all happening in the context of a cosmos that's mostly empty space and mysterious phenomena. That doesn't make your problems unimportant. Your life matters. Your experiences are real and valid. But there's something freeing about knowing that you're part of something much larger. Something strange and beautiful and full of mysteries. Every photon of light that hits your eye traveled from a star. Maybe a star in our galaxy. Maybe a star in another galaxy, millions or billions of light years away. That light has been traveling through space for eons. It crossed unimaginable distances, and it ended its journey by hitting your retina, allowing you to see. You're connected to the cosmos. The atoms in your body were forged in stars that died billions of years ago. You're made of stardust. That's not a poetic metaphor. It's literally true. The carbon, oxygen, nitrogen, iron in your body came from stars. And now, you're living in a time when we can study the universe. We can build telescopes, collect data, analyze it, and learn about the cosmos. We can discover strange things that challenge our understanding. We can push the boundaries of knowledge. That's a privilege. For most of human history, people could only look up at the sky and wonder. They couldn't measure distances to stars, or detect radio signals, or observe the cosmic microwave background. We can. And every strange discovery we make is expanding what's possible to know. One of the hardest things about studying the universe is learning to live with questions that don't have answers yet. In our daily lives, we're used to getting answers quickly. If we don't know something, we can look it up online in seconds. We're used to immediate information. But the universe doesn't work that way. Some questions take decades to answer. Some take centuries. Some might never be answered, at least not in our lifetimes. And that's okay. That's part of what makes science fascinating. Think about the wow signal again. It's been almost 50 years. We still don't know what it was. That's frustrating. But it's also a reminder that the universe operates on its own timeline, not ours. We don't get to demand answers. We have to wait for the right observations, the right technology, the right ideas. This patience is actually valuable. It teaches us humility. It reminds us that we're not entitled to understanding everything immediately. The universe is under no obligation to make sense to us on our schedule. And while we wait for answers, we learn other things. We develop new technologies. We train new generations of scientists. We make observations that might not answer the original question but reveal something else interesting. Science is full of accidental discoveries. Things we found while looking for something else. The cosmic microwave background was discovered by accident. Pulsars were discovered by accident. Even penicillin was discovered by accident. So while we're puzzling over the wow signal, or Tabby's star, or any of these mysteries, we're also doing other work, making other discoveries, learning other things. The mysteries are important, but they're not the only thing we're doing. This is something non-scientists don't always understand. They sometimes think scientists are wasting time on unsolvable problems. Why spend decades studying something if you can't figure it out? Why not move on to easier questions? But the unsolvable problems often turn out to be solvable eventually. And even if they're not, the process of trying to solve them teaches us things, develops new methods, reveals unexpected phenomena. The search for dark matter hasn't found dark matter particles yet. Decades of searching, billions of dollars spent, no definitive detection. Some people think this is a failure, but it's not. The experiments designed to detect dark matter have improved our understanding of particle physics, developed new detector technologies, and ruled out many hypotheses. Even failed searches teach us something. The same is true for these cosmic mysteries. Even if we never figure out what the wow signal was, the search for it has advanced radio astronomy, developed better methods for analyzing signals, and taught us to think carefully about what evidence for extraterrestrial intelligence would look like. Tabby's star has taught us that stars are more complex than we thought, that there are behaviors we didn't anticipate, that we need better models of how dust behaves around stars. Even if we never definitively explain its dimming, we've learned valuable things in the attempt. Science isn't just about getting answers. It's about the process of asking good questions, developing methods to investigate them, and following where the evidence leads. The mysteries are part of that process. They're not obstacles, they're opportunities. We're nowhere near the end of discovery. Astronomy is a young science. We've barely scratched the surface. The universe is full of things we haven't found yet. Future telescopes will be more sensitive. They'll observe more of the sky, more often, in more wavelengths. They'll detect fainter signals, more distant objects. Each new observation has the potential to reveal something unexpected. Maybe we'll finally figure out what the wow signal was. Maybe we'll detect another one. Maybe we'll find definitive evidence of intelligent life elsewhere in the universe. Or maybe we'll discover we're alone, which would be just as profound. Maybe we'll figure out what's dimming Tabby's star. Maybe we'll find more stars like it. Maybe we'll discover a whole new category of stellar phenomena. Maybe we'll understand odd radio circles. Maybe they'll teach us about galaxy evolution, or supermassive black holes, or something we haven't even thought of yet. Maybe we'll find more giant structures that challenge the cosmological principle. Maybe we'll have to revise our understanding of how the universe is organized at the largest scales. Maybe we'll solve the mystery of the CMB cold spot. Maybe it'll turn out to be a supervoid after all. Or maybe it'll be evidence of something more exotic. Maybe we'll figure out Przybylski's star. Maybe it'll lead to discoveries in nuclear physics, or reveal something about how stars work that we didn't know. Maybe we'll detect more interstellar objects like Oumuamua. Maybe we'll get better data on them. Maybe one will be obviously artificial, or maybe they'll all turn out to be natural, teaching us about planetary systems around other stars. Maybe we'll understand fast blue optical transients. Maybe they'll teach us about black hole formation, or neutron stars, or stellar collisions. And maybe we'll resolve the age of the Methuselah star. Maybe our models will improve, or our measurements will get better, and the tension will go away. Or maybe we'll discover new mysteries, things we can't even imagine right now. Phenomena that will puzzle future generations of astronomers the way these mysteries puzzle us today. That's the beauty of science. It's an ongoing process. We're not trying to have all the answers. We're trying to ask better questions. We're trying to push the boundaries of what we know and understand. So tonight, when you go outside, take a moment to look up. Look at the stars. Think about the fact that some of those points of light are actually galaxies, collections of billions of stars, millions of light years away. Think about the fact that somewhere in that vast expanse, there's a star dimming in ways we don't understand. There's a void that's almost empty. There's a signal that appeared once and vanished. There's an interstellar object speeding through the darkness. There are explosions brighter than we thought possible. There are structures larger than theory says should exist. The universe is strange. It's full of mysteries. And every mystery is an invitation to wonder, to question, to explore. We're lucky to be alive at a time when we can study these things. When we have telescopes powerful enough to detect them, when we have the knowledge and technology to even recognize that they're strange. 400 years ago, none of this was possible. 400 years from now, we'll know so much more. But right now, in this moment, we're on the frontier. We're pushing the boundaries. We're discovering strange things in space and trying to figure out what they mean. That's an incredible privilege. And it's happening right now. Not in some distant future, not in some science fiction story, right now. In our lifetime. So when you look up at the night sky, remember that you're looking at a universe full of wonders. Some we understand, many we don't. And every strange thing we discover is a reminder that the cosmos is far more interesting than we imagined. The journey of discovery continues. The mysteries remain. And somewhere out there, in the vast darkness between the stars, there are strange things waiting to be found. Things that will puzzle us, challenge us, and ultimately teach us something new about the universe we live in. That's what makes astronomy so exciting. That's why scientists stay up late, analyzing data, building models, trying to explain the unexplainable. Because the universe is strange, and strange is wonderful. Let me leave you with one last thing to think about. Every mystery I've talked about tonight represents something real, something that's out there right now. The wow signal happened. Tabby's star is dimming. Odd radio circles exist. These aren't hypotheticals, they're observations. And here's what that means. The universe doesn't care about our theories. It doesn't care about our models or our expectations. It just does what it does. And when we observe it carefully, we find things that surprise us. That's both humbling and exciting. Humbling because it reminds us how much we don't know. Exciting because it means there's always more to discover. Science isn't about having all the answers. It's about being honest about what we don't know. It's about looking at the evidence and admitting when we're puzzled. The scientists studying these strange phenomena aren't embarrassed that they don't have explanations. They're excited because mysteries are opportunities. Every unsolved problem is a chance to learn something fundamental about how the universe works. Maybe some of these mysteries will be solved soon. Maybe others will remain unsolved for decades or centuries. Maybe some will never be fully explained, but that's okay. The universe doesn't owe us easy answers. It is what it is. Our job is to observe it as carefully as we can, measure it as precisely as we can, and try to understand it as best as we can. And when we can't explain something, we say so. We admit we don't know. We keep observing, keep measuring, keep thinking, because that's how progress happens. Not by pretending we understand everything, but by being honest about what we don't understand. The strangest things we've discovered in space are strange precisely because they don't fit our current understanding. They're outliers, they're anomalies, they're puzzles. But puzzles can be solved. Maybe not today, maybe not tomorrow, but eventually, with enough observation and enough thought, we figure things out. That's the story of science. A story of mysteries gradually being solved, revealing a universe that's stranger and more wonderful than we imagined. So the next time you hear about a strange discovery in space, don't think of it as a problem. Think of it as an opportunity to learn something new, an opportunity to expand our understanding. Because the universe is full of strange things. Some we've found, many more we haven't. And each one, when we discover it, teaches us something. That's the adventure of astronomy. That's why people dedicate their lives to studying the cosmos. Because out there, in the darkness between the stars, mysteries are waiting. Strange signals, dimming stars, giant circles, impossible structures, ancient voids, cold spots, radioactive elements that shouldn't exist, interstellar visitors, unexplained explosions, stars older than they should be. These are the things that keep astronomers awake at night. Not because they're scared, but because they're fascinated. And if you've made it this far in this video, if you've listened to all these strange stories, then maybe you're fascinated too. That's good. The universe deserves our fascination. It deserves our curiosity. It deserves our best efforts to understand it, because it's strange, wonderfully, beautifully strange. And that strangeness is what makes it worth studying. Thank you for joining me on this journey through the strangest things we've discovered in space. If you enjoyed this exploration, a like or subscribe would really help the channel grow. And remember, the universe is full of mysteries. We've barely begun to understand it. There are strange things out there waiting to be discovered. Things that will puzzle and amaze us. Things that will challenge everything we think we know. That's not a problem. That's a promise. The universe is strange. And we're lucky to be here to witness it. Sleep well under the stars. And remember, somewhere out there, strange things are happening. Things we don't understand yet. Things that, one day, might change everything we know about the cosmos. Good night.